Black holes stand out as highly destructive cosmic entities. Anything that comes too close to the central singularity of a black hole, whether it's an asteroid, planet, or star, faces the risk of being torn apart by the extreme intensity of its gravitational field. If the object gets close enough to cross the event horizon of the black hole, it simply disappears without ever reappearing, contributing to the increase in the black hole's mass and expanding its radius in the process. There is nothing we can hurl at a black hole that would cause the slightest harm. Not even another black hole will result in its destruction. The two will simply merge to form a larger black hole, releasing energy in the form of gravitational waves in the process. According to some theories, the universe might eventually consist entirely of black holes in a very distant future. However, there is a possibility of destruction or evaporation of these objects, as proposed by the theory. If the theory is correct, all we need to do is wait. Hawking radiation. In 1974, Stephen Hawking proposed a process that could lead to the gradual loss of mass of a black hole. Hawking radiation, as it came to be known, is based on a well-established phenomenon called quantum fluctuations of the vacuum. According to quantum mechanics, a given point in space-time fluctuates between multiple possible energy states. These fluctuations are driven by the continuous creation and destruction of virtual particle pairs, each consisting of a particle and its oppositely charged antiparticle. Normally, these two particles collide and annihilate shortly after appearing, preserving the total energy. However, when they appear near the event horizon of a black hole, something peculiar happens. If they are positioned just right, one of the particles can escape the gravitational pull of the black hole while its counterpart falls in. It then annihilates another oppositely charged particle within the event horizon of the black hole, reducing the black hole's mass. Meanwhile, to an outside observer, it would appear as if the black hole emitted the escaped particle. Thus, unless a black hole continues to absorb additional matter and energy, it will evaporate particle by particle at an extremely slow rate. Black hole thermodynamics suggests that we can similarly define the temperature of a black hole. The more massive the black hole, the lower its temperature. The universe's largest black holes would give off temperatures on the order of 10 to the 17th power Kelvin, very close to absolute zero. Meanwhile, one with the mass of the asteroid Vesta would have a temperature close to 200 degrees Celsius, thus releasing a lot of energy in the form of Hawking radiation to the cold outside environment. The smaller the black hole, the hotter it seems to be burning, and the sooner it will burn out completely. But don't hold your breath for it to happen quickly. First of all, most black holes accrete or absorb matter and energy more quickly than they emit Hawking radiation. Even if a black hole with the mass of our sun stopped accreting, it would take 10 to the 67th power years, many magnitudes longer than the current age of the universe, to fully evaporate. When a black hole reaches about 230 metric tons, it will have only one more second to live. In that final second, its event horizon becomes increasingly tiny until finally releasing all of its energy back into the universe. And while Hawking radiation has never been directly observed, some scientists believe that certain gamma-ray flashes detected in the sky are actually traces of the last moments of small, primordial black holes formed at the dawn of time. Eventually, in an almost inconceivably distant future, the universe may be left as a cold and dark place. But if Stephen Hawking was right, before that happens, the normally terrifying and otherwise impervious black holes will end their existence in a final blaze of glory. Nuking and antimatter. The explosive attempts to unravel black holes. Black holes, those enigmatic cosmic behemoths, possess a gravitational grip so potent that anything venturing too close risks being shredded to pieces. Even the mightiest forces like asteroids, planets, or stars succumb to the inexorable pull of a black hole's central singularity. Should an object dare to traverse the black hole's event horizon, it vanishes, contributing to the black hole's mass growth and expanding its cosmic dominance. In the realm of theoretical destruction, we ponder the efficacy of nuclear explosions and antimatter assaults. By detonating the world's nuclear arsenal around a miniature black hole, we witness a grand spectacle. Yet, this cataclysmic event only amplifies the black hole's mass and size. Antimatter, known for annihilating its matter counterpart, proves futile against the black hole's deleting ability. Regardless of whether an object is made of matter or antimatter, the black hole assimilates it, growing more massive with each intrusion. Anti-black hole conundrum. Seeking annihilation? Envisioning the clash between a black hole and its antimatter counterpart stirs excitement. Particle symmetry suggests that an anti-black hole possessing the same mass but opposite charge might yield spectacular results upon collision. Alas, the laws of charge conservation prevail, resulting in a new, larger black hole devoid of charge. Breaking the event horizon, a radical approach. Contemplating the very fabric of black holes, we explore the notion of dissolving the event horizon. Just as a spinning black hole repels nearby objects, an extreme amidst these audacious attempts to unravel the secrets of black holes, a radical approach emerges, destroying the event horizon. When the black hole spins at excessive speeds, an anomaly occurs, dissolving the event horizon. This revolutionary phenomenon challenges the notion of a cosmic prison, allowing nearby objects to escape the inescapable confinement of the singularity. However, this proposal does not come without its dilemmas. If we succeed in destroying the event horizon, we are faced with a naked singularity, a challenging spectacle for the understanding of physics. The singularity, usually hidden, emerges before us, defying predictability and causality. The fabric of space-time tears apart, undoing the boundaries between space and time. This radical rupture in the fabric of reality makes witnessing the singularity an unknown. What would we witness before this unfathomable source of infinite gravity? Unpredictability reigns, challenging our fundamental notions of physics. A naked singularity defies the laws governing our known universe. The scientific community remains divided on the viability of this bold endeavor. Some believe that nature prohibits the formation of naked singularities, imposing the creation of an event horizon to preserve the sanity of the cosmos. The event horizon, an invisible boundary that conceals the singularity, may indeed be a necessary guardian for the coherence of our physical understanding. Thus, as we contemplate the possibility of destroying a black hole, we are confronted with the prospect of unleashing anarchy on the foundations of physics. Perhaps, in our quest for knowledge, wisdom lies in accepting the safer method: waiting. All black holes emit tiny particles known as Hawking radiation, causing a slow loss of mass until their eventual evaporation. This patient approach is the only one we know to destroy a black hole: to wait. So yes, it is possible to destroy a black hole. Waiting is the key. We don't need to wait billions of years. There's a fascinating world to explore here and now. While we await the slow evaporation of black holes, there's a vast universe of exciting discoveries within our reach. So if you like the content, please smash that like button and subscribe so you don't miss the next videos. Bye!